Okay, so we're going to get this party started. My name is Kevin Newton, and I would like to formally welcome you all to the, if this is going to turn on, hold on a second. Aha, welcome to the live keynote. Yeah, I want to thank Mats for the introduction. Since we're in the keynote room and I'm the first person speaking here, I feel like I have this privilege to just say, welcome to the live keynote. Apparently that joke's not landing, so that's okay. You can laugh if you want. Just a little pity laugh would be appreciated. Okay, cool. Anyway, my name is Kevin Newton. I work at Shopify. I work on the YJIT team, along with Aaron, Alan, Noah, and Maxime. If you want to talk about that or any other thing, come and find me at the booth. We're the nerds with the green background. So yeah. I'm going to open up with a quick... Oh, this thing's dying. I'm going to open up with a quick warning. So I talk pretty quickly when I'm nervous. I am nervous. I've had a lot of caffeine. We're going to talk pretty quickly. I'm also going to say, if you're a junior developer, please don't leave the room. This is a somewhat complicated topic. I've spent hours agonizing over this, trying to make it accessible for everyone. So if you're a junior developer, don't leave the room. If you're a senior developer, please stay with me. I promise there's content in here for you. It's not at the very beginning, but it will be there. So I want to talk to you about parsing Ruby. I want to talk to you about how Ruby has been parsed over time, how we get from plain source text into a structure that we can deal with. But in order to do that, I need to back up and talk about the fundamentals that underlie those concepts in order to give you an understanding of how these things work. I need to give you the theory before I can give you the practice. So here's the game plan. We're going to build a grammar for a simple language. I'll explain what a grammar is in a second. We're going to build a parser for a simple language. We're going to look at the history of the Ruby parser and how that has evolved over time and how it's used. And finally, we are going to look at how Repressor works, which is an internal library, standard library that is used to gather information from the parser as it is parsing. So first step, building a grammar. A grammar is a syntactical representation of what is allowed in a language. Language here is used kind of loosely. It's not English, it's not Ruby, it's just a language. It's any kind of concept that puts together a series of tokens. So if we look at, and we just wanted a language that only accepted one single number, this is what the grammar would look like. It's actually overly complicated for this because it could just say program points to number, but I'm doing this for illustrative purposes. A program is going to be our root node. It's going to point to our overall grammar. It says the only thing that it accepts in this grammar is a number. The number is a non-terminal token as opposed to a terminal token, and it accepts only a single number token. I realize I just said token a whole bunch of times. This will accept something like 1 or 2 or 7 or any number, but it's not extensible enough for us to do anything with, so I'm going to extend it a little bit. We're going to add the ability to do addition. Now, when we're doing addition, we are now accepting a number plus a number or just an individual number. So now we can accept a couple things. We can accept 1, we can accept 1 plus 2, but we can't accept 1 plus 2 plus 3. Why? There's no recursion here. All right, so we need to extend it a little bit further. This is now, if I clicked the right thing, this is now a little bit of recursive. So, right, so this is now left recursive is what we say in the theory. This is pointing at itself. The expression node in the tree is pointing at itself. It can go and accept more and more information. It accepts 1 plus 2, now accepts 1 plus 2 plus 3. We can extend it for subtraction and go all the way as far as we want. It's infinite, right? This is left recursive. We can continue on and make another one. We can make another rule that includes terms. This is the reason we're splitting this up and not making it into expressions is something I'm going to explain in a second, but that's called operator precedence. We'll get into that. But the function of this is to accept another set of rules. And if we put it back into our grammar so that it will understand itself, it can recurse down all the way, understand plus, minus, times, divide. The last step, the last thing you want to add to this is going to be parentheses. This kind of language can accept 1 times 2. You have to do a little bit of substitution in your head. You say, okay, 1 times 2 is the entire language, right? Okay, a language is an expression. We go down to the expression, we say an expression is just a term. A term is a term times a number. A term is a number, so it's a number times a number. Stay with me. I promise this is going to make sense in a second. The last thing we want to add is parentheses. This one's a little fun. This is any single token or symbol in this language can be made into an overall program, because you see a program is equal to expression by wrapping it in parentheses. So you can put it anywhere in our language. All of a sudden, we support parentheses. This is our grammar. This is what we're going to use throughout this presentation to understand this language, to build on top of it. All right, so we've got our language. The next step is going to be building a parser that understands this language. The grammar was a abstract concept. We're going to now implement that. So this is our source. We're going to take this source file. This is your .numbers or whatever language you want to call it. We're going to loop over it in Ruby. It's going to be a language implemented in Ruby. We're going to say until the input string is empty, we are going to click our mouse is what we're going to do. Come on. We are going to switch over the input. We're going to skip over white space. And the little $ apostrophe there means skip over the last match. We're going to go and take our numbers, anything that matches that regex, and we're going to yield out a number token. Same thing with these operators. We're going to yield out that operator token. That $& means take the last match string. And finally, we're going to throw a parse error if we don't understand any remaining syntax. The important part is here. This is called lexical analysis, tokenization, any kind of thing like that. There's a lot of names for it. The point is that we are taking these segments of the file and yielding out individual tokens. Okay, so if we go and we parse this and we execute it over this source string, we're going to find a number plus all of these different tokens as we build them up. And now we have our list. This is what was parsed by that file. Everyone with me? I see some nods. Yes. Oh, more nods. Excellent. Great. Okay, so this is called a token stream, or a token buffer, or just a list of things. And we're going to take this token stream and we're going to pass it through our grammar. So at this point, we have tokens. We have the concept of lexical analysis. We don't have semantic meaning yet, so we're going to add that. So it's called accepting the input. We're going to run through how it works. This is our grammar. We already went over this. We're going to add a stack. And this stack is going to be a token stack. And it's also called the semantic stack, semantic meaning stack, semantic token stack. People really don't like having one name for things. But what it's going to do is it's going to take the first token, and this is called shifting. We are shifting a token. We have shifted it off of the list of input tokens. And then we're going to say, okay, we have our token. What are we going to do with it? We need something equivalent to it in the terms of our grammar. Okay, well, we can see from our grammar that a number is equal to a factor. So we are going to replace it with factor on our stack. That thing we just did is called reducing. Shift and reduce. Those are the two terms I'm going to add to your idiolect today. So we're going to shift more tokens, continue shifting until we get to something else we can reduce. Okay, we've got a number. We can reduce that again using our grammar down to a factor. Continue shifting, continue shifting. Again, we get a factor, and finally we get to something we can actually do. Now this stack is looking a little bit large, and I've been working for Aaron for a little bit, so I couldn't resist just showing that this is in fact overflowing. So we can go and take the factor, and we can say, okay, a factor is actually a term. A term minus a term can just be an expression. As it gets reduced further, we can go through this process and just keep substituting things. If we ever get to a point where we can no longer substitute something or shift a token, then we throw a syntax error, right? We continue down this process. We look at the various rules. We continue to shift. Overall, we finally get to the end of our input. We substitute, we substitute, we substitute, we substitute, we substitute all the way down to program. At this point, we have accepted our input, and this is a valid syntax for our grammar. The thing that we just did in taking those tokens and passing it through this process of semantic analysis, of going through that stack and replacing them over the course of time with shifting and reducing, it turns out that that's very repetitive. It turns out that that's language agnostic. It doesn't have specific meaning. It's just something that we can do over and over again. And in the late 80s, early 90s, the thing in vogue to do if you were building a language was to use a parser generator. A parser generator is a program that takes that kind of grammar and those kinds of actions and does that for you. Not to say it does everything, but it takes the shifting and reducing part out of the need of your head using very, unfortunately, large integer arrays. Anyway, what this would look like with a parser generator. So Ruby has a parser generator in the standard library. It's called rack. There's a reason for that. I'll show you in a minute. And it looks something like this. This is a parser generator using rack. The thing up top that we're looking at is the operator precedence, up where it says left. Left is associativity. I'm not going to get into today. But that operator precedence tells you if you have to determine between a shift and a reduce, that you're going to go with the operator with the higher precedence. The expressions down there are actually an equivalent grammar to the grammar we already have. When you pass a grammar into a parser generator, it's going to take that and do all that shifting and reducing for you and generate it for you. The last thing that you can do on top of this is you can execute actions when rules are reduced. So when rules are reduced, you can do something. This one is going to evaluate it immediately. This is going to take whatever the input is and just evaluate it as soon as we find it. So if you find an expression plus an expression, you're going to do the value plus the value. You can also do something like this, which is building up a syntax tree. This is what was done in Ruby before 1.9. We built up a syntax tree, and then in order to execute Ruby, it walked over that tree and understood what it was doing over time. This is as opposed to building a bytecode interpreter, which is what Yarv was in Ruby 1.9. If we take this file and we pass it through rack, and we build our file, and we go into IRB and we require it, and we parse it, you get this. This may not look like much, but it's kind of interesting because if we blow it up a little bit, this is actually a tree. This is a syntax tree. This is what we have built using our parser generator. If you look back at the source, you can see how that relates to it, and it takes care of precedence for us. Right, this was our original grammar, and this can build that kind of thing, and we're going to come back to this. Okay, we're actually on track here for time, so it's good progress so far. So the next thing I want to talk about is the history of the Ruby parser. Now, the reason that it's called rack, the parser generator that the standard library uses, is because Yak was the original one. YACC, yet another compiler, I believe. It's a parser generator that was built way back when, and it was in vogue in 1993 when Matt started using it for building out the Ruby parser. So in the very, very early days, this is the earliest changelog entry I could find, Ruby 0.06 in 1994. I had to go through the Wayback Machine and find a tarball that had a changelog that was entirely Japanese, but I found it. So it's there. For the first pre 1.0, all of the changelog entries are in Japanese. So I had some fun with Google Translate. There's some fun things in here. Ruby didn't used to look like Ruby. Ruby used to look like both Python and C++. The top one there is saying that dicts are hash literals, and he added like braces for hash literal syntax, which didn't used to exist. It's a backwards incompatibility because that used to be array syntax back in, whenever it was. Rescue was misspelled for about 90 versions. It got renamed to rescue, like the correct one. That in Japanese, that's saying that it was embarrassing. So I feel badly, sorry, Bats, but I thought felt like including that. After a while, I guess we got up to Ruby 1.0. Ruby 1.0 started looking more and more like Ruby. The superclass syntax went from being a colon like C++ to a less than that we recognize in Ruby today. The continue keyword went from being continue to next, which we also recognize from Ruby today. They added syntax to access the singleton classes. We started getting regex flags that were specific to encoding, which was kind of an interesting thing because at the time, a lot of stuff was very Western-centric. I love the fact that Ruby was written in Japan because we have encoding kind of as a first-class citizen, especially in Ruby 1.9. Ruby 1.3 comes out the day before Ruby 1.2. I know that's confusing. The odd versions were developer releases and were used to be development branches effectively. This was SVN, or actually, I don't even know if it was SVN yet. But we get a couple of interesting things like body statements like begin, rescue, else, end clauses. We get indental here docs. The next day, Ruby 1.2.0 is released. And more and more things. The true and false keywords were added for the first time, which is kind of a funny thing to add to a language in Ruby 1.2. %W array literals, stuff like that. The next year, we get Ruby 1.4. We get binary number literals, a couple of other interesting things. Multi-byte character identifiers, again, with the multi-byte strings. This is something that Ruby was ahead of time on. Ruby 1.5 had compile time string concatenation. I don't know if you know this, but in a Ruby file, if you put a string and then a space and then another string, it becomes one string when Ruby parses it. Kind of a weird thing, came from C. The reason I have it in here is because it was on the to-do list since Ruby 0.06. I don't know why. I mean, it's great, I guess, if you like that kind of thing. The next year, we get the rescue modifier form. Modifier means inline, so like foo rescue bar. And finally, the next year, we get node dump. Node dump is not a Ruby version. Node dump is a project that came out of the Pragmatic Programmers, and it's a C extension to Ruby, and it's written in English in the US. And this is kind of interesting because Ruby is starting to pick up steam and starting to get some popularity. Node dump was an extension. So at the time, Ruby before 1.9 was a tree walk interpreter, meaning it took the AST that we already built up like we looked at, it walked over it and interpreted it as it went. Node dump took that AST and printed it out in a human readable format so you can understand it. This was the first attempt, to my knowledge, to take the Ruby AST and do something with it that was not execute Ruby. Ruby 1.7.1 comes out. This was right around the time of the first RubyConf. And we get some interesting things, break and next now accept values, rescue and singleton method bodies, more and more things are getting added. Around this time, JRuby gets created. So it's funny. So JRuby takes the parse.y file, the grammar file that we looked at. You remember the rack file from earlier. It takes that grammar file, takes all of the action blocks, which were the things in the braces, and rewrites them all. And I love this. I love just thinking about this. Like, what would make this language better? If it were written in Java, that would be better. And at the time, it was. I mean, JVM is still one of the greatest inventions we've ever done as programmers. It's incredibly powerful, and it's achieved better peak performance numbers than YARV at the time that it was introduced. But the interesting thing about this is to take this file, to take these things. Okay, a one-time translation is one thing, but how are you going to stay up to date? You're not. It's freaking hard. You have to watch the commits on parse.y and just stay up to date. You got to keep translating. And that's a hard thing to do. And, tons of props to the JRuby team for keeping up with this, because this is not an easy thing to do. And the reason I'm harping on this and taking time here is because this is what you have to do in order to maintain another parser in Ruby. You have to watch the commits on this file and just make it work. So I'm gonna come back to that point later. Around this time, Ripper 0.1 is released. Minero Aoki publishes it on his website. It takes the grammar file, rewrites it to dispatch parser events and scanner events instead of building the AST that Ruby 1.7 would build. Still to this day in the documentation, it says Ripper is still early alpha version. That's what it says in Ruby 3.1.0. It's been 20 years. Still early alpha. Maybe we'll get to beta someday. Ruby 1.8 comes out 2 years later, and we get a couple more interesting things. I'm going to start skipping through this a lot faster, so if you thought I was going fast now. Around the same time, Parse Tree gets released. Parse Tree is a project by Ryan Davis that builds out an AST from the source file using a C extension. It relies on Ruby 1.8 internals, so unfortunately, Ryan had to deprecate this when Ruby 1.9 came out because it completely changed to a bytecode interpreter. Rubinius comes out about this time. Rubinius is a very fascinating project, rewriting the standard library and rewriting Ruby in Ruby. It bootstraps Ruby. Unfortunately, it is not, at this point, what it was at the time. It's no longer kind of up to date. It's a different project at this point. But there are a couple of interesting things like having to rewrite, again, those action blocks in Ruby. I included Cardinal because it's a very interesting thing. It's a rewrite of the Ruby thing, except this time, instead of taking the parse.y file, it actually took the grammar. Mats had published a grammar, the abstract grammar that we looked at on a website way back when. And this was a fork of the Ruby 1.4 grammar, and they rewrote it in order to put it on the Parrot VM. Iron Ruby was written around this time for the .NET framework. Finally, Ruby Parser comes out. Ryan Davis rewrites his parser so that you can use it with Yarv in 1.9. Completely had to rewrite it and used Rack to generate it. Around this time, Yarv comes out. Yarv is a PhD thesis that is a bytecode interpreter for Ruby. It upgrades a couple things. It changes it so that instead of using Yak, it uses Bison, which is just a successor that has a lot of the same functionality. Ripper is merged into the standard library. We'll show how that works. And a couple other of controversial things are done at the time, including symbol hash keys and lambda literals. Ruby 1.9, we keep moving along. We get the Ruby Intermediate language, which is a research project that rebuilds the Ruby parser in OCaml. If you were wondering of the list of, if you had your list of bingo languages of places that Ruby had been rewritten in, okay, I doubt OCaml would be on your list, but there you go. Ruby 1.3's release is the last of the 1.0 series, and these two standards are recognized by the International Committee as international standards for this language. We get into the Ruby 2.0 series, and we get all kinds of fun things. We get refinements. We get %i symbol lists, keyword arguments, Ruby 2.x keyword arguments, not Ruby 3.x keyword arguments. And finally, we get the Parser Gen. The Parser Gen is from White Quark. It is a published gem with a parser API that uses Raggle to generate, using another parser generator to build out an AST. This one has stayed up to date miraculously over time, and you can see this is a very short list of a very short abbreviated list of all the different tools that are built on top of this gem. Shuffle Ruby comes out around this time. I'm going to start skipping through these. Ruby 2.1, we get required keyword arguments. 2.2, dynamic symbol hash keys. 2.3, we get here docs. The frozen string literal pragma. Around this time, everyone starts freaking out about memory, and they start opening PRs to Rails saying .freeze, 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 .freeze. The entire pull request is just .freeze. Finally, we get the frozen string literal pragma, and people can calm down with that. We get the 2proc, so you can call refinements with 2proc. We get top-level return, multiple assignments, and conditionals. Around this time, a project comes out called Tree Sitter. Tree Sitter is a very interesting parser project, a parser generator library that is used mostly for IDEs. And it has a plugin for the Ruby grammar that is not all the way there, but it's enough that you can use it for like go-to definition on GitHub. Typed Ruby comes out around this time, which is a type system written in Rust. The parser is written in C++. I included this because it's kind of interesting. They basically forked the grammar, the parse.y from Ruby. They took the lexer from Ruby parser, and then eventually Sorbet, when they wanted to have a Ruby parser, they just used this one as well. 2.5 comes out with Restio and Assure at the block level. 2.6 comes out. Ruby VM abstract syntax tree is introduced. Ruby VM abstract syntax tree was not what I would call an intentional release. It was part of a test suite for another feature. And it's a very, very interesting thing. I encourage you to go to the Ruby issue tracker and go read about it. It's another form of a parser that can be used, though it's unclear if it's going to be supported in the long term or how it's going to be supported. It might do some optimizations before it hands things back to you. Not entirely clear. Flip-flop is deprecated, much to the chagrin of flip-flop fans everywhere. 2.7 flip-flop is undeprecated, so it's okay. Yeah, we get a lot of introduction of syntax in Ruby 2.7, as you saw in Matt's keynote. Method reference operator was added, method reference operator was removed. We get some interesting syntax for like ** nil for saying this method accepts no keywords, right word assignment, number parameters, argument forwarding, all of these different things. Finally, Ruby 3 comes out. Happy about Ruby 3. We get keyword arguments that are different keyword arguments. Previously, the keyword arguments were based on allocating a hash, and then there was a whole bunch of syntax errors. It was very confusing. Now we get some actual separated keyword arguments. We get endless method definitions. You can do def foo equals bar, and that is all working. We get some interesting pragmas for raptors, and we get keyword pattern matching in single line. Ruby 3.1, preview 1 came out today. There you go. Yeah, all right. We get some hash literal syntax, hash literal shorthand so that you don't have to write the value in a hash. This is somewhat like JavaScript. And we get, in pattern matching, you can pin expressions, not just variables. Okay. That was the abridged history, believe it or not. I have a website. I will share with you a link at the end that has way more information with way more implementations of Ruby, and you can go and click around to your heart's desire. I got 5 minutes left. I want to tell you how Ripper works. Ripper is a standard library. It hooks into the parser. It gives you events. We go back to our grammar. We go back to our Parser Generator. We see this is our lexer down at the bottom. It's our grammar up at the top. Ripper is going to hook in here, and it's going to hook in here. What that is to say is when Ripper finds a token, a token initially, it is going to fire a scanner event. I'm using this in quotes because that doesn't really mean anything to a lot of people, but it's a scanner event. Up top, anytime a rule is reduced, you remember when I showed you what reduced meant at the beginning? It's going to fire an event whenever a rule is reduced. So you're going to get events for these different things. I'll show you the syntax for what that means. Internally to Ruby in the source, this is in parse.y. You can see how this kind of works. It found a comment, so it's going to dispatch a scan event for that comment. Okay, so we can go and we can build a subclass of Ripper. We can say on comment. We're going to build the subclass. We're going to add an adder reader for comments. We're going to have this on comment. This is how you handle an event in Ripper. You define this on method. There are 200 some odd methods. I will show you the link to the docs later. If we go and we build a parser with this source, we tell it to go and parse itself, and then we pull the comments back out, you will get a list of comments. This is how you can use Ripper in your own thing if you want to go and pull tokens out. It's a lot easier on the token side than it is on the node side, and I'll show you why. Remember that I said it hooked into these different spots. Up top, it's hooking into the reductions of the rules. So this is also in parse.y in Ruby, and this is the part of the grammar that is handling the super calls. Whenever you call super, you can call super with no arguments, or you can call it with arguments. And you might see in the faint font that weird comment. This is how Ripper works. Ripper has comments all over the parse.y file. Ripper then builds its own parse.y file based on this file using those comments, using macros. Yeah. It takes those comments and then builds its own parse.y file, which it can then dispatch different events. The important part is right here. That's a DSL. It's a tiny little language that's baked into the language parser generator that is using by Ruby that then gets generated by Makefile, which then gets generated by Ripper. I couldn't tell you that again if I tried. If we go and we try to build a parser using Ripper to handle this, and we go and we pass in this stuff, we build these handlers for these events. ZSuper took no arguments, super took one argument, and we tell it to go parse. We'll get this. Super called without arguments, great. ZSuper worked just fine. Super called with arguments, and we get nothing. Why did we get nothing? If we go back to our grammar, we can see, okay, actually, this is being passed an argument. What argument is it being passed? It's being passed the paren args argument. Remember the way that this works is as things are getting reduced, whatever value you have for that node gets passed up the tree. We didn't implement a handler for those events, so we get nil. So, okay, we have a problem. What are we going to do? Ripper ships with two subclasses. There is sexp builder, S-expression builder, and S-expression builder PP for pretty printer. It has an implemented handler for every single one. Using method missing, it's a whole thing. If we go and we call it with this subclass, we actually will get something that looks a lot like the AST we built earlier, right? So what are your options? If you want to use Ripper, you can implement every method handler yourself, which is fine. You can do it. You can inherit from Ripper Sex Builder or Ripper Sex Builder PP, or you can do some combination of both. As we saw with the comment handler earlier, it just worked. You can just get your tokens out. It's fine. I have implemented one for you. It's here. It's in Prettier, and it's, you know, it's there. It happens. There are 200 some odd tokens. There is a hash for each of them. I'm actively working on upstreaming it so that you can have one for yourself. If you want to build a syntax tree, what are your options? To this day, Ryan is still maintaining Ruby Parser. This is an option for you. It has some community option. It's not 100% compatible, though he did just bring it up to Ruby 3.0. New stuff may break because it's not shipped with core. The Parser Gen, tons of community adoption. It backs RubyConf. It backs standard, which is a wrapper around RubyConf. It's very well documented. Not 100% compatible necessarily. New stuff may break. Every time new syntax comes out, they have to play catch up. It's just part of the name of the game. It doesn't ship with or test with core. So, I mean, that's just what it is. RubyVM abstract syntax tree, it's still too early to tell what's actually happening with this. It's on the issue tracker. You can check it out. It's not implemented on any other Ruby implementations. So if you're interested in portability, don't choose that option. Finally, there's Ripper, as we talked about. It's built into the Parser Generator. It's well tested in core. It ships with Ruby. There's no documentation. In the last hack days for Shopify, thank you, Shopify, I spent a fair amount of time, and there is now documentation for every event, and with an example for every single one that will trigger all of those events. You can go and find it. I will send you the link. It is here. All of that is to say, the Ruby uses a parser generator. It originally used Yak. It now uses Bison. Parser generators are complicated technologies that use shift and reduce operations to build up syntax trees. Parser generators are difficult to maintain across implementations of languages. They're not the most intuitive of technologies, and it's difficult to maintain upstream compatibility. It's a good thing that Ruby is going to slow down on syntax and feature development because it's going to give an opportunity for all the other Ruby implementations to catch up. But this is not something that we can solve as a community without the help of core. This is not something that we can really fix without having a standard library parser, because as you saw with the massive list of tools that I went through, all of those went away when the money dried up. You can only keep up with core for so long. It's exhausting, and you have to have the parser ship with Ruby. That's really the only option. So Ruby VMAST or Ripper, those are the options. I'm pushing for Ripper, but I'd be happy if we just had one that was standard that RubyConf used, so that we could all get used to that and use it. And yeah, I hope this inspires you to learn more about syntax trees. I hope this inspires you to build more tools on Ruby. We're here to answer the call that Matt's just put out to build more tools. And yeah, that's all I got. Thank you very much.